Hello, everyone, and thank you for joining us at Machina today. My name is Zeke Arlott. I lead our Frontier Technology division here at Metric Search. We are a private equity-backed recruitment organization, and for the last 7 years, I've recruited into the physical AI sector, and I'm pleased to be leading this panel today on the topic of hardware. And is hardware a commodity now? And if so, where does the value truly lie? I'm joined on stage by an exceptional panel spanning core robotic building blocks, and I'll let Cecile introduce herself firstly.
Hi, everybody. I'm Cecile Schomllgruber, co-founder and CEO of Stereolabs. So we make cameras and AI vision for robots.
John?
Hi, everyone. Great to be here. My name is John Kourentis. I lead go-to-market activities in the physical AI business unit at Arm.
My name is Robert. I'm one of the co-founders and chief robotics officer at Dexterity. We build logistics and physical AI for logistics and warehousing. Some of our key products are in things like truck loading, truck unloading, palletizing, depalletizing, and so on.
Hello, my name is Rob Knight. I'm Chief Robotics Officer and co-founder at UMA, where we are trying to make the world a better place with robots for everyone.
Right. It's great for everyone to be here. I think the key talking point here today on this topic is that while certain components within hardware are becoming increasingly commoditized, core robotics building blocks still remain highly specialized and are far from commodity. I'll pose a high-level question to the panel here, to each of you firstly, and that question is, Cecile, firstly, in your opinion, what components are not yet a commodity?
Of course, I come from the camera, ecosystem. So definitely, I've been working on cameras for 15 years, trying to replicate how we as humans perceive the world. And I can tell you, we haven't, reached the level of accuracy that we have. So there's a long way ahead of us before we reach the performance and the quality that we need for a perfect replica of the physical world. So yeah, definitely cameras are not, commoditized yet.
John, what's your opinion on that?
Zeke, probably not going to surprise you that I'm going to say compute, right? But if you think about the world of autonomous robots, right, we look at two particular areas of compute that are really, really complex. One is what we call perception-driven intelligence. So that's a robot's ability to understand where it is in the physical world and navigate through that environment accordingly, right? And the second area is what we call interactive-driven intelligence. So looking at the human-robot interface, primarily going to be voice in most scenarios, and that voice interaction requires a lot of contextual awareness. It probably requires understanding of sentiment. It has quite a high level of reasoning capability attached to it. So if you think of those two areas, perception-driven intelligence and interactive-driven intelligence, they are really, really complex compute problems. We're really scratching the surface of how to apply those effectively into autonomous robotics platforms. So those two areas, particularly in the overall sense of compute, I'd say are a long way from being commoditized.
Thank you, and we'll delve into each of these topics in more detail, but we've got the full stack guys over there. So Robert, you first. Where do you see where's hardware not a commodity right now?
Yeah, I'll give a twofold answer. The first one I was just going to say is cameras and compute, unsurprisingly. And truly, the difficulties are in thermals, in size. Running these robots out in the field, you don't really have cloud connectivity. You want data to be transferred from your imaging sensors. We've got a dozen or so running 10 plus gigabits per camera. It is a lot of data to transform and then create action out of. And so having the right physical interface to bring in that data and then having unified memory and strong floating point operations to run models or even an LLM on board is highly critical and is the next step for us. And this has been a huge problem over the last several years. And I think the other aspect for us is going to be in hands and grippers. It's still very up in the air what's the right answer, but also the reliability and resilience and robustness of these gripping technologies is very important. You can't be replacing things in the field every 2 or 3 weeks.
Yes, indeed. Hands remain a serious challenge. In terms of the bodies themselves, I think we're quite near to a low-level commodity with QDD drives. It's not that hard anymore to buy them off the shelf. You can get parts machined online. You can just mail order them. They turn up. You can screw them together. You can run Isaac Sim. And testament to that is the hundreds and hundreds of companies that are now producing humanoids, and they're walking around and doing stuff. Hands magnify all of those problems. We don't really know what the answers are. We don't really even know what the questions are. And everything is smaller and more compact. And on top of that, tactile sensing, what you do with it, what formats we should use, that's still a serious way to go. And it's going to become a major bottleneck at some point. At the moment, that's not what's stopping everything advancing. But there will come a point, I think, where that will really be what holds it back.
Interesting. And humanoid hands and fine dexterous manipulation is something that we'll definitely delve in on in more detail later on in the panel. I think one of the talking points I wanted to discuss with you two in particular, being full-stack roboticists at Dexterity and at UMA, is with regards to hardware and software being defined and constrained by each other. You know, well-designed hardware can augment or reduce the burden on an AI model or on software. So I'll start with you, Robert. What design decisions have you made on the hardware side to improve AI model performance on your deployments there at Dexterity?
Yeah, that's a good question. So a couple points. Let's just take one of our leading applications, truck loading, for example. Humans were never really meant to be working on these types of very difficult tasks. And in fact, a lot of the labor that we're trying to augment and potentially replace with automation is things that weren't ever meant for humans. And you'll realize a lot of the ergonomic difficulties that humans have, robots, and especially humanoid robots, also have. And we've had the need to increase the dexterous capability of robots significantly, both their strength, their ability to bend and be flexible in tight environments and get through things, and as well as move extremely fast. And so if you look at our robot system, we call it the mech, they're 8 degrees of freedom per arm. There are 2 arms, and they're fairly strong with 30 kilograms of payload, 5.4 meters of reach, and they can still work collaboratively and cooperatively in a tight environment like a small shipping container. And this is really difficult. And we have experimented with a lot of off-the-shelf stuff over the years, and the models, the planners, the algorithms, they really struggle when you don't have the right hardware. And so I think the key thing that you have to realize is there's a bar for feasibility, and then there's a bar for what I call superhuman effort, superhuman ability, and that's what makes customers and the actual application powerful and customers willing to actually use your robots. And so it really takes another level of hardware innovation, kind of looking back at your models, what's not working, what's slowing down, and then perfecting the hardware so that your models can perform even better. And so I think the shape of the robot, the strength of the robot is highly critical in a lot of different applications. And you can actually share a lot of that technology in a set of applications, but I don't think there's one form factor that's good for all applications.
That's interesting. The need for superhuman performance, not just human performance, but going above and beyond that to improve efficiency. I'll ask the same question to you, Rob. Obviously, you've been designing hardware now for 25 years. So what have you seen in terms of hardware advancements improving model performance?
The advent of QDD drives and the MIT mode helped a lot with smoothing out that whole process. You're seeing technology that came across from drones, much higher power densities, lower costs. We're going even deeper into the component level. When you talk to the manufacturers, it takes a certain amount of investment to get the volumes up, to bring down the cost of some solution, and they themselves are waiting to see which solution will work the best. So you have an interaction there as well. I'm a big fan of tendon-driven hands, and it's still a very open question for me how you can control those with some of these techniques. Most of the sim-to-real approaches which work so well for walking, they have a simplified approach, and when you try and actually convert that into a more complicated mechanical system, that causes a lot of issues. Sorry, I'm not quite sure what the question was again.
It was about novel electromechanical designs and how that improves or augments model performance. So I think you've covered that there.
Yeah, no, definitely. So for the larger body, where you're looking at the larger joints, the QDDs have made a huge difference on that. But when you come across to the hands, it has a lot of problems with heating, and it doesn't transfer as well. So for the large actions and the kind of hyper beyond human performance, machines can be better for that, but for the fine dexterous tasks, that's still an open question.
So it seems that there's still a long way to go in kind of the hardware side of things, whether that's dexterous hands or whether that's novel form factors to improve the kind of actual performance of the robotic platform. So in that sense, if it's still playing such an important role in improving performance or differentiating the product, it cannot be said that hardware is a commodity right now. I'd like to move on into the sense that robot performance is not just achieved by system design choices, but also kind of subsystem level at the compute and at the sensing level. John, a question for you and Arm would be, how critical are advanced CPUs for modern robotics?
Yes, super critical. Actually, if you think about, in the world of physical AI, probably the key metric to care about is the latency between sensing and actuation, right? And the systems that bridge that capability are actually, there are multiple systems, and there's quite a lot of complexity in there. And that sensing to actuation needs to happen in milliseconds. It needs to happen in a reliable way, have some degree of determinism, have safety and security applied to it. And so, if you think about the systems that are involved in bringing all of that together, require high levels of real-time performance, require very efficient AI execution of AI workloads, and require functional safety and security all to come together. And at the heart of all of that are CPUs. They're orchestrating all of those systems, and they're present in all of the systems across the robot that performs all of those tasks, from sensors to actuators to the main brain. So I'd say, CPU is critical in the orchestration of all of that system capability.
And I want to draw a parallel between the autonomous driving world, where maybe they're a couple of years ahead of robotics and humanoids in particular. What we've witnessed in the AV industry is the AV companies co-designing silicon to meet the design constraints in their realm. Do you expect the robotics industry to follow suit?
We expect a blend, in the same way that we see in the autonomous vehicle industry. Companies will make decisions based off of primarily, the key things that are driving those decisions are what's the use case that they're really focused on, or the application that they're really focused on. What are the kind of volumes that they have to play with, and what does that mean in terms of the business case that they have? And so they're the kind of the four fundamentals that drive the decision whether to do in-house vertically integrated silicon or whether to take off the shelf. Some companies will take off the shelf available silicon because that will be the fastest path to market. There's a time to market advantage of doing that. Others will want to go fully vertically integrated and design their own silicon so that they can optimize for a specific workload. Talk about software, hardware, co-design at a hardware level. In some instances that will really help. But it's a very kind of individual choice for each of the companies whether they go off the shelf or invest in building their own silicon teams and bringing their own silicon to market. Fundamentally, tying all of those things together is the need for very efficient compute, safe compute, secure compute, and that has to be done whether you buy off the shelf or in-house. And it needs to be capable of kind of scaling and expanding to a growing world of high performance AI workloads that need to be executed on those platforms. So whether, regardless of the decision you're making, you have to have that as your key consideration, is how you're going to be able to really efficiently run those workloads, and those workloads are going to be potentially individual workloads for a particular company. Regardless of which way you go, ARM has an ecosystem of 22 million software developers, right, building software around ARM, and so whether you're building in-house silicon or taking ARM-based silicon off the shelf, there's already a full suite of optimized software, tools, AI frameworks that are already highly optimized to be deployed for development and deployment on ARM-based systems. So regardless which way you go, you've got a huge ecosystem ready and waiting to deploy onto your platform.
Thank you for that. And then moving on to the sensing side. Again, I think advanced sensing is going to be a key robotic building block in unlocking advanced performance. Cecile, that is what Stereolabs are doing. You're developing a sensing and perception platform for physical AI. what role do you see in advanced sensing for improving robotic performance and deployment?
Yeah, it's a very exciting time, I have to say. So we started this company 15 years ago. So we've seen the early stage of robotics, and the evolution that we've seen for the past couple of months is incredible. There are so many companies, popping up every day with new ideas and new approaches, different types of use cases. For us, of course, at the core, there is vision and perception, because obviously the machine needs to see and understand the world around the machine. So we have been focusing on this for years. And I forgot the question, Zeke.
It was regarding advanced sensing and what improvements do we need to see?
Yeah, exactly. So we have been working on this for years. So the objective is to have the exact replica of the physical world. And so we not only sell cameras, but we provide the software. So it's a hardware and software combination where we focus on, of course, latency, because this is very important, resolution, frame rate, the depth, accuracy, localization, uncertainty estimation. So those are all the things that we are focusing on at the moment, and this is why we call it advanced, because if you can take two cameras that share the same CMOS sensors, but they can perform dramatically different. And this is what we're focusing on. And as you said, like safety is becoming crucial, especially in some application. So there is a whole new world for robotics, and it needs to reach this level of accuracy and safety that is hard to reach today. So there's a lot of work, and this is what we're doing today with so the company we fused with Ouster beginning of the year. So they are building LiDARs. They have been building LiDARs for a long time. So combining both was really important for us, because we have customers who come to us and say, "Oh, what vision or perception system should I use?" And it's always the customer always makes the decision, and they're not perception engineers, and we have been doing this for years. So our idea with Angus, the CEO of Ouster, was to say, "Hey, come to us, and we'll find the best solution for your application, for the type of machine you have, and so we can really optimize and give you the best product." So yeah.
Interesting. And I like what you said there about the camera solutions as well as the LiDAR solutions coming from Ouster. I again want to draw a parallel with the AV industry, that again is a couple of years ahead of maybe the robotics industry. A critical issue there is sensor cost as well as sensor size and the integration of the sensor into an AV platform or into a robotic platform. Are you seeing similar requirements in the robotics industry for smaller and more cost-effective sensors?
Yeah, of course. I mean, people are asking for this, but the performance is more important than the cost and the size today. So they want sensors that perform 24/7, that doesn't stop, that gives a precise depth estimation on the whole range. Our customers do sensor fusion, so they have a LiDAR, they have different cameras, 2D cameras, 3D cameras. They have one, ARM-based computer with a GPU, and everything needs to work. So we are seeing that we need to focus on the system, not only just the modules today, because every module can work, by itself. But when you combine 8 or 10 cameras, and you want to have a high performance system, this becomes much more challenging. So we always have this approach of, making sure that everything works together. And
And you mentioned it there already, actually, but sensor and compute integration is becoming more and more important. What are you doing there at Stereolabs on that topic?
I mean, we definitely work hand in hand with NVIDIA and ARM. Our compute, especially for us, because we sell the hardware, but all our software tool is on the host computer, and we definitely work very closely with NVIDIA. So, of course, as I said, it's a system. So we not only develop cameras, we think about the system that our customers are going to use, and we want to. And the cost becomes important here because the compute costs are increasing very fast. So this is something that we always make sure it's important to understand the cost that the machine needs to have. It depends. If you have a small robot that costs, you sell it for $1,000, of course you're not gonna you're going to decide on different type of compute and different type of sensor. If you have a larger machine, as we see at Dexterity, for example, they have different expectations. So we need to have this flexibility, and sensors and compute definitely work together. You can have one without the other one. So big optimization here.
Thank you. And John, we've spoken about this, and I think Cecile just covered that, but you expect an evolution in sensors for physical AI applications. How do you see that impacting compute requirements moving forward at Arm?
Yeah, I think I'd echo a lot of what Cecile said. If you think about where we are in the life cycle of very capable autonomous, humanoid, quadruped robots, we're fairly early on in that life cycle. So there's a lot of exploration happening. I think as we move more towards commercial scale out, we're undoubtedly going to see cost reductions in some of those sensor types. Most humanoids have LiDARs on them today, and they're fairly expensive components, right? So as you go to more towards commercial scale out, we could probably expect that lower cost LiDAR sensors are going to come into play. There will be scenarios where you only have vision sensing. You have a fairly constrained environment, maybe a factory floor that's well understood and well mapped, and maybe just vision sensing is enough, and you don't need a LiDAR. But in terms of optimizations in respect to compute, I think there's a tendency to think that as we on this path to create more capable autonomous robots, we need to throw more compute at the problem, we need to throw more advanced AI models at the problem. But the reality is these systems are really constrained by two critical factors, power and thermals. And on a humanoid robot, you're limited in terms of battery capacity, and you're limited by the amount of actual physical cooling, active cooling that you can have and mount onto the robot. So those two things being the limiting factors leads us to think that actually there's a big piece of work to do in terms of overall system optimization. I think we've all kind of touched on the point in different ways here, but that system optimization, being able to efficiently run AI models on a constrained environment with battery and power, thermals taken into account, I think is really the next big thing. So it's taking that complete sensor to brain and actuator system and making that entire pathway more efficient, and being able to deploy models in a very, very efficient way that run very efficiently on that main kind of NVIDIA platform, whatever the main brain of the computer is.
Thank you. And it's interesting you mentioned that. We've seen a wide array of robotic form factors out there today, and you're fortunate enough to visit a lot of robotics labs around the world. What have you seen in terms of novel designs to improve compute or improve power efficiency? I'm
fortunate that I do visit a lot of robotics labs. I think one thing I would say is that there is a carpenter somewhere making a lot of money out of building wooden staircases that go to that lead to nowhere, deployed all over the robotics labs in Europe. But on a serious point, I think there are certain design choices to be made in terms of the form factor of a robot. There's a lot of focus on bipedal humanoid robots, but in a lot of applications that probably may not be required. Depending on the use case and the application, it may make sense to have a humanoid form factor but on wheels. That probably is a safer platform to be around, particularly around in an environment with lots of people around. Probably safer, but also allows you the capability to maybe put more compute into the base of that platform. Or more battery capacity into the base of that platform. So I think there, a lot of exploration in terms of form factors going on. They ultimately, as we've said already, all of those things are going to be driven by the specific use case of the robot. We were talking about a robot deployed in a hospital application environment earlier. Absolutely makes sense for that to be on wheels and not a biped, right? Because it's walking into oncology, children's oncology units, and it's much safer to have that on a fixed wheelbase than as a biped. So a lot of the form factor choices will be dependent on the end use case and application for the robot, I think.
And we'll stay on the topic of form factors, and we'll speak to Robert and Rob over there about their form factors. You touched on it earlier, your customers, Robert, FedEx in particular, looking for superhuman performance for their deployments. What novel approaches have you taken? You mentioned about the additional elbows, but can you share more on that topic?
Yeah, I'll again give a twofold answer, both from the compute perspective as well as from the mechanical perspective. When you've got to move in tight spaces and you want to be able to both compute faster your motions as well as execute them faster, we've had to go through a lot of optimization on robot shape and robot strength. It's really like a trade-off. I liken it to like building a rocket. You have to always carry your fuel to the next stage, and you can build a bigger rocket, but you'll have to carry more fuel, and so it's a race to the bottom. And the similar story goes for robotics as well. You want a stronger robot, you want stronger wrists, you'll have to carry those motors at the end, your distal end of your robot, and so your base joints are going to have to be much stronger or much heavier. And so there's a delicate balance of how much strength you need, how much dexterity you need, and playing with that as well as understanding from the manufacturer's perspective. We work with Kawasaki, for example, what is possible and what isn't possible. That creates a very unique Pareto optimal for us to be able to choose the right shape and the right strength for the robot. We generally look for a little bit better than OSHA requirements, right? OSHA only says you can lift, 22 pounds or 25 pounds until you get to 2 people that can lift double that. And we want to be able to handle at least 2 people's worth of tasks. We don't need to do too much beyond that, but we don't want to go too low as well. In terms of compute, though, again, we're very power and thermal constrained, but we have so many imaging sensors from RGB in depth, and LiDAR, and the data is very dense, and it's tens to hundreds of megapixels of data flying in all the same time. If you're going to sequentially go through all of them, it is impossible to make a decision. And the problem with, say, neural networks and a lot of things is you're spending your brain power on all the data all the time, and maybe 90% of the data is not very useful. And so I've got to give a cue to programming frameworks like CUDA and whatnot to be able to really easily ingest the data in parallel, filter out or create features from the important aspects, ignore the not important aspects, so you can give your model a chance to actually perform well without having to waste your flops on absolutely everything. And getting the data from the camera into the memory layout, and that is possible for that parallel computing directly in one stage without any sort of transformations, and then programming your compute to be able to use that memory layout has been super important to be able to handle the influx of all of that data and make a decision really fast. So really good programmability, really good parallelism, really good direct sensor to memory transfer has been completely revolutionary for us. And then, of course, apply the right mechanical design, and you can build a very superhuman robot in both decision-making speed as well as actual execution speed.
Thank you for that. And there's one thing I want to hone in on there in particular, and I want to ask the question to you, Rob, because we spoke about it earlier. And that question is regard to actuators. Actuators play a key role in robotic movement, acting like the muscles of humans, essentially. What is the situation with actuators right now, and are they a commodity?
Up to a certain level, they are. If you look at some of the open source projects we did, they're just using off-the-shelf actuators. There's definitely a gradient, though, and if you want to push up to higher performance, you can't just go and buy those. You can't order those online. Going back to the general point you're talking about now, though, for me, what I'm thinking as you're talking about these things is that there's a tension between the specialization and the generalization. It's always been sensible to make specialized machines because you can hone them and you can ignore data you don't need and you can focus them on the task at hand. But the kind of vision we're talking about, where you can elevate a society through mass generalization of automation, can that be achieved through a series of specializations? Or do we have to fundamentally move towards a technology we don't yet have? And as everyone's talking, it makes me wonder if we just keep sequentially making more and more specialized machines, surely that's heading away from generalization. So that's the kind of tension I think we need to address. It makes sense. If you want to do a certain thing, you design it a certain way, you can make it superhuman. But this machine which can do all of these things that we want, so that you can really alleviate lots of different tasks, and you can swap them into lots of different roles. I wonder if we can get there the way we're presently going.
Exactly, and that's something Robert and I discussed actually, that generalist robots, I think we're still very far away from, but robots for specific tasks is possible and are being deployed across the US and across Europe now. I want to touch on some of the key areas that maybe humanoid robots in particular lack on, and this was something, Rob, you and I discussed. Rodney Brooks, who's probably developed more humanoid robots than anyone else in the world, he believes that deployable dexterity, so dexterous manipulation hands, are pathetic. His words, not mine. But is that another example of hardware, being crude in comparison to what we are capable of as humans?
Yes, I suspect it probably is. All of the problems are magnified when you try and make them into hands. It's smaller, it's more compact, the thermal gets harder, the power gets harder. And again, if you look at it from a civilizational level, our civilization was literally built by hands. So if we're going to enable this next era, then we have to solve this problem. The physics ends up that you either have to, is it easier to get rid of heat or is it easier to transmit mechanical power? Both have their issues, particularly in maintenance for tendon-driven systems. But Rodney talks about deeper problems, that we don't have even a language to describe what it means to be dexterous. We can't describe tasks. We can't therefore talk coherently about the data we need. We can't really even describe the problem yet. So that's where he's coming from. But he's quite a pessimistic fella, if you've ever met him. I'm more optimistic, but maybe I'm just naive. I like to think that if we have enough innovation and we have enough collaboration, that these techniques can be applied and that something will emerge from it which is more than we are expecting. So we're just going to keep pushing it along, and hopefully we can do it faster than he thinks we can. Certainly that's what we're going to do. But that's partly because I enjoy designing hands. So we just keep designing and building them, and we keep applying techniques. But you can look at how LLMs emerged. But it was laughable, even a few years ago, to think that we could do what we can do now with AI. It was pipe dream. And then all of a sudden, it pops up. And suddenly we're taking these things very seriously, and they're designing medicines, solving protein problems, and we can do real things with them. So things can emerge if we have this collaborative system, if we have a lot of people working together on these hard problems. As hardware prices continue to come down, we get some aspects of commodification, we get shared benchmarks. Then I'm hopeful that we will get there faster than he thinks.
Thank you for sharing that. And I'm conscious on time, we're running towards the end, but I think to summarize this across sensing, across advanced compute, across certain key robotic building blocks, hardware is still not yet a commodity. And I think the old refrain is true. Hardware is hard, but hardware and software are still constrained and defined by each other. And we really need to champion the next generation of hardware builders, because they will play an integral part in enabling the safe and mass deployment of physical AI systems. Thank you for joining us today. It's been a pleasure to host this panel, and enjoy the rest of Machina. Thank you.